Okay, let's go and get through our lecture for today where things are kind of winding down. There are really just a couple topics left that I want to cover this semester that we have time for anyway. I really wanted to get into some of the GPU computing. I wanted to do some MPI programming. But so far, all we've done is stuff in Python. So I wanted to give you a little overview of concurrency in C and C++. Because part of the motivation for concurrent programming is to have improved performance. And Python, as an interpreted language, is not really the ultimate in high performance computing. So I want to give at least a brief overview of doing concurrent execution in both C and C++. So let's go ahead and take a look at that. That's what we're going to talk about today. And one of the things is that just like in Python, in C and C++, there are really a couple ways we can go about getting concurrent behavior. One is by having multiple threads, same concept as in Python. The other is by having multiple processes. And multiple processes, the real difference there is threads are all within one same single process memory space, allocated memory block, meaning they can share global variables, they can share data. Whereas if we create separate processes, those are going to be in their own completely independent, isolated memory spaces. The processes could still communicate, but they're all kind of walled off from each other in their own memory unless we implement shared memory of some sort. Now, there's no conceptual difference between those and what we've seen in Python. There is one difference, though, is that in C or C++, it compiles to native code, meaning it's native machine code specifically organized for the processor that you compiled for and the system that you compiled for, meaning there's no interpreter. There's also no GIL. In other words, there's no global interpreter lock involved there. So that creates this thing where you can have a higher level of concurrency than you can have in Python because the processes really are, or the threads can really run independently. Now, in processes, multiple processes, they're completely separate. It's up to the operating system to schedule those as separate processes under the OS. But either way, where we have concurrent behavior, we have to be careful to use synchronization between processes, communicate between the processes or threads where necessary or where appropriate. Okay, so let's dig in. Let's start off with multiple threads. And we probably won't get to multiple processes today. We might look at multiple processes next class. Or I might just give you time to work on your labs for next class. I haven't decided yet, but I'll post on that. But the multiple threads here, the idea is we want to spawn and manage multiple threads. Now, there's a couple ways to do that. One is kind of using a threading library, which is kind of the old way of doing that. It's been around for quite a while. Specifically, there's a version called POSIX Threads or Pthreads that we're going to talk about. That's kind of considered the old way. And then the new way is starting with C++11 and C11. Threading was added to kind of the C standard language facilities. In other words, they decided that threading is really an important part of programming. So rather than relying on this library to do all of that, let's build it into the language itself. So let's make it part of the language. But that, if you're using a compiler that does not support C++11 or C11, then we would have to resort to doing this the old way. So let's start with looking at it the old way. All right. So prior to C++11, there was nothing built into the language that allowed us to do threading. We have a library that had to deal with threads for us. So that library that became kind of the standardized way of doing that was called Pthreads. And the P in Pthreads stands for POSIX. And for those of you who don't know what POSIX is, POSIX was kind of and is a kind of standard for programming interfaces for Unix-based operating systems. And it kind of, essentially, if you made a Unix-based operating system and you followed the POSIX standard for how to do things, then your operating system would be compatible with other Unix-based operating systems without having been written by the same people. So the idea was it wasn't a way for implementing the stuff as much as it was, this is what the API should look like to do things in the operating system. And part of that standard was the standard for how you create threads and manage threads in a program. And that's where Pthreads came from. It's the POSIX implementation or definition of how a threading system should be implemented in the code API that you use to interact with that. And that created this kind of standardized way of doing threading, and that has kind of Pthreads has gone beyond Unix-based systems into Windows and other operating systems. But the idea is to use that in a C program, we just need to #include pthread.h. And then we just have to know what functions it has. So it's a function library, just like every other C library. So this just has a collection of functions in it that we can then use to do stuff. So that pthread library, let's start off with creating a thread. So the function to create a thread is pthread_create. And the way that works is we pass some things into it and it will create a thread. Now, what do we pass into it? The two that are probably most important is this thread, pthread_t. That's a thread type. And that's used to create what we could consider or think of as a reference to that thread that we create that we can then use later to do things with that thread. So in other words, there's no variable name associated with it, but we're going to create one ourselves here. It's going to return to us, hey, think of this as like a thread ID that this returns. Now, the second thing here are the attributes we want for that thread. Right now, we're not going to concern ourselves with all the attributes, but the two important ones here, this is a function pointer to the function we want that thread to start with. Think of this coming from the Python world as where we said target equal and gave a function reference. That's the same kind of thing here. And then this is kind of like the args equal where we gave it the list of arguments. This is a void pointer to whatever arguments we want to pass to this start routine. So the start routine can be started. We can pass arguments to it. That's going to return to us this thread ID pointer that comes in or gets assigned here. And then we'll have a thread that gets created. Now, if this thing is successful, it'll return a 0 as the return value. If it fails, it'll return some error number that says why there was an error. It could be threads aren't supported on this machine. It could be that there's already too many threads. There could be a number of reasons why this would fail, and you can look up those error codes. But the idea is if this returns a 0, we now have a thread. It has started running that thread. We don't have to do a start like we did in Python. It'll start it automatically. This is the routine that starts up. Now, there are attributes you could pass to say delay starting it, or we're not going to concern ourselves with that right now. Let's look at a couple of the other functions. To join a thread, meaning to wait for it to complete, we pass that like thread ID pthread_t thing that was filled in here. And then we can have this pointer to a void pointer that is kind of the value that thread returns. So this is a distinction here that's different from how we implement this in Python. Is that notice the threads here can actually return a pointer to some data back to us by assigning that pointer value into here. It's a void pointer, so you could point it at a structure or an integer or a character pointer to a string. You could make this return all sorts of different types if you want, including something complex like a structure with multiple things inside of it. But the thread is just going to return an address of that block of data that is the return value to us, so we can get that data back. Now, we don't have to have a return type here, but we can. And also notice here that if that's successful, if the thread was joined successfully, that'll return to 0. And notice that pthread_join, it'll block and wait until the thread, the target thread, the one we specified here, terminates. So in other words, if we hit pthread_join, we'll be running through our execution. It's going to stop and say, wait for that function, that thread to finish. When that thread finishes, we will now have its return value, and this will return a 0 saying it's successfully completed. Now, there are cases where this could fail for other reasons and we cannot get a 0. But for the most part, you're going to get a 0 return saying, hey, that thing completed. And the only way we're going to get past this function call is if that thread has terminated, completed. Okay, and then from inside the thread, to exit the thread and return that value, notice we can do put the void pointer here to the value we want to have returned, and we just call pthread_exit. Now, you don't really necessarily have to call pthread_exit. but notice that if you do call it, it immediately terminates your function or your thread that executes that function, returning this value. Now notice that it down here though it says an implicit call to pthread_exit is made when a thread other than the thread in which main was first invoked returns from the start routine that was used to create it. So in other words, what this is saying is that if we return from that thread function, then it will automatically do a pthread exit for us. And also notice it continues on this next sentence. The function's return value will serve as the exit status for that thread. In other words, you could just have a thread return normally rather than call pthread_exit, and it will automatically kind of implicitly call that for us. And the return value of this function, there is no return value because it never returns. As soon as I call pthread_exit, that terminates the function, the thread right there. This function will never return a value back because it never returns back to the caller. It kills the thread that called this, so the thread is now gone. Okay, probably the best way to understand this is to look at a quick example here. So notice that the only thing that I had to include is pthread.h. I make these two, these are function prototypes for my two thread functions that I'm going to create. Notice that I have them, a void pointer is what's passed to them, a void pointer is what they return, and that matches how pthreads wants its threads to be set up. And then down here, I have this pthread_t type for thread 1 and thread 2. This is to hold the kind of thread IDs that we talked about for those two threads. And then down here, I start the threads by calling pthread_create, and notice I pass the address of this one because it's going to fill in the ID for us. And then null is the arguments or the options attributes. I'm not passing any attributes, so it's okay to put null there. Here's the function thread_func1. That's the pointer or the address of that function. And notice here I'm passing a void pointer null in for the arguments, meaning I'm not passing anything into that function. So in other words, here I'm not passing any arguments to it, but I could, if I wanted to, put some data type here as long as it evaluates as an address that passes that through. So I could pass an address of a structure to that. I could pass an address of an integer, an address of a character, like a string to that function. So in other words, when this thread function 1 starts up, I could pass the data to it if I wanted to. So I start both threads. They start automatically as soon as I create them. And now continuing on in this example, then I join both threads. And when I join them, remember they can return a return value to me. One of the things I should do is free that because if that was allocated inside of that function, we need to return it or free it when we're done with it. So in this case, I wasn't really returning anything useful here, but if you did return it, make sure you free that so we don't end up with a memory leak every time we create a thread and it finishes. Now, if we get to here, both T2 and T1 have finished, and we're done with that. Now, what do the threads themselves look like? These are the thread functions. Notice I just have this void pointer of something being passed in. In our case, I'm just passing a null pointer in, but we could change it to something else. And we have this returning a void pointer. In this case, I'm just returning null with pthread_exit. And notice what each of these functions is doing. This is just going through 100 times and printing out a 1. And I also flushed it so the 1 gets pushed out rather than buffering until we get a new line. And then down here, I go from 100 times and print a 2. So I'm going to see thread 1 is going to print 1s. Thread 2 is going to print 2s, but those are going to be running kind of concurrently. So let's look at what our output would look like. So in our output, if we run that, it starts the threads. We get, notice this mixture of 1s and 2s happening here as it runs those two threads. And then both of them eventually finish, causing the joins to continue. And here, both threads finished. Now, if we run it again, we'll get a different output. Notice this one started with 1, 1, and then 3 2s. This one did 1, 2, 2, 1, 2. Notice they both finished with kind of a string of 2s at the end. But notice the output is different. And that is, again, with any kind of concurrent system, we have kind of that non-deterministic behavior happening there. And that means if we have non-deterministic behavior, there are cases where we're going to need to control that. We're going to need to synchronize that in some way. So Pthreads has some synchronization mechanisms. We need to be able to control the way those threads kind of carry out their flow and synchronize them. So we already saw one of them, pthread_join. We saw that back right here. And really, you just put the thread ID in there, and then it can return something to us. Now, but there are other ones. There's a mutex, which is essentially the same as a lock that we've seen in Python. And then there are also condition variables, which are the same as condition objects that we saw in Python. Now, those are analogous to mechanisms we've seen before. Let's go ahead and take a look at mutexes. So mutexes, in this case, they're pretty much identical to lock objects we've been using in Python. They're just called a mutex. So here, to create one, you do pthread underscore mutex underscore t. That's the mutex type for pthreads, mutexes. And I just give it a name, a variable name, like mutex1. And then I started off with this pthread underscore mutex underscore initializer when I create it. So that creates a kind of blank mutex that is initialized as being unlocked initially. Now, how do I use it? Anywhere that I want to lock it, I call pthread underscore mutex underscore lock. I pass a pointer to the mutex or the address of the mutex into that. That will lock it. And then to unlock it, I call pthread underscore mutex unlock and pass it. So I would surround some critical section. So here's some critical section I don't want to be interrupted, or I want to synchronize. I can lock and then unlock afterwards, just like with locks that we saw previously. We can have as many mutexes as we need. You could have more than one of these variables. We could have mutex1, mutex2, mutex3, and they would all lock with respect to themselves, but not each other. So we could create some fairly complex synchronization mechanisms using mutex. And notice that we could have as many threads as we want kind of using this, because I declared it in this global space here. So this thread could use that lock, another thread could use that lock, and so forth. Okay. Now, pthreads condition variables. If you remember what a condition variable is, it basically allows us to unlock temporarily while waiting for some condition to happen. And then when that condition happens, we can reacquire the lock and then continue on about our business. So looking at this, a condition variable is always going to be associated with some lock that we want to free while waiting and then reacquire once we get back into this. So the idea for that is probably best shown in an example. So here's an example. I've created both a mutex, because I'm going to need that, because that's the thing I'm going to free while I wait. And then I also create this pthread underscore condition underscore t, a condition variable. And I'm just calling this condition underscore cond here. And that's pthread underscore cond initializer. So I create both of those. That starts off with the lock in the locked state, or in the unlocked state, or the mutex in the unlocked state, and it's going to start off with a condition variable in the not waiting state, or kind of free state. Now, in code where I want to release that, I acquire my lock, and then I would have some kind of while that says, while the condition we want to wait upon is, so while that is true, so in other words, we might say, while the buffer is empty, we want to wait, or while the buffer is full, when we're trying to put something in wait. And we've seen those kinds of design patterns previously in Python. It's the same thing here. But notice the way you use this condition variable is we call pthread underscore cond underscore wait when we want to wait. We pass in the address of the condition variable and the address of the lock. And what this is going to do is this is going to free that lock, but then wait on this condition, or block on that condition variable. When that condition variable gets signaled, it's going to reacquire this lock and then continue on. So here's where we put the condition protected action. The lock would be reacquired here. When we're completely done with it, we can unlock there. Now, let's look at the signal side of this, which is the thing that wakes up or releases this wait. That's going to be the same kind of thing, except we call pthread underscore cond underscore signal, and we pass the condition variable. Notice we don't have to pass the lock in here to this. We can just pass that condition variable in. And notice that there are two versions of this. There's pthread underscore cond underscore signal, pthread underscore cond underscore broadcast. And those are basically like signal or signal all that we saw in Python. Same concepts. Okay. Now, that was using pthreads. And there's some other stuff in pthreads that I didn't really cover. If you're interested, look at the pthreads.h header file, or look at the documentation. There are some other functions in there that are probably worth looking at if you're going to do some serious thread programming. But that's kind of the basic idea of creating threads, joining threads, having them return things, passing things to them. and then having synchronization between them. Now, in C++11, there's kind of a new way that they added to do this. So they added kind of concurrency support directly to the standard language itself. So it's not this add-on library that comes from the Unix world. They actually said, let's build threading right into the language itself. And C++11, these features extend into C++17 and C++20. So all the stuff we're going to look at will work in anything C++11 and later. There's some newer things in C++17 and C++20 that have been added. We're going to focus on the ones in C++11. All right, so let's take a quick look. But notice that means we don't need to use POSIX Threads anymore. We don't need to use the Pthreads library. We can do stuff directly from the language itself. All right, so here's kind of a roadmap of things that have been and are being added. That notice with C++11, we have threads that are now part of the language itself, mutexes and locks, thread local data, condition variables, tasks. So all of this is there. In 2014, they added kind of these reader and writer locks, which are a different kind of lock than we had before. And then you'll notice kind of continuing on into C++17, they added some standard template library things to do parallel algorithms, meaning that you don't have to write all of that yourself. There's some parallel sorting algorithms and searching algorithms and things like that that were added in 2017. And then in 2020, there's kind of latches and barriers, coroutines, futures, these atomic smart pointer things, task blocks. So there's some new features that are being added to new versions of C now. But we're going to focus on kind of just the threads and mutexes that we looked at previously in Pthreads and how to do that here. All right, so let's just jump right into an example here. And this example is really kind of the same example that we did previously with Pthreads, but notice this is done in the new C++11 way. One thing to note that I should mention is you can also do this in straight C11 too. C11, you don't have to do this in kind of the object-oriented way. You could do it in a standard straight C way with C11 and later as well. All right, but here, let's do it in the kind of object-oriented way, C++11. So pound include, rather than pthread.h, we just did in pound include thread. That's all we have to include. And then we create our functions. Notice we don't have to have the weird void pointers here. These can be any kind of function with any return values, any kind of argument list. Here I've just made them both void to keep it simple, to match what we did before. And then down here, notice I'm using this namespace standard. If we didn't have this namespace standard using line here, we'd have to put std : in front of cout and end l and thread. But I'm using the standard namespace. Notice the threading capability is part of that standard namespace now. All right, so to create a thread, I just say make a thread, give it a variable name t1, and then pass to it, its constructor, the function pointer of the function I want it to start with. So much easier in some ways in Pthreads that I just say, hey, make a thread, call it t1, start it with this function. That starts them both. This joins them both. So if I get past that, they're both done. Same code as we had before. And then continuing on, you'll notice the functions look just like they did before in the previous example code, but we don't have to have void pointers here. These can be any return type, any argument type. And if I were to want to pass arguments to these thread functions, let me go back just a second, we could do that in this constructor here. When we create that, we just put comma and then list all of the arguments that we're passing to this thread function. Pass that to the constructor for the thread objects when they get created. Okay, so relatively straightforward. Creating both of those threads. This will work the same as the previous one. All right, so let's quickly look at synchronization in C++11. And in this case, for synchronization, we have a standard type that's part of the that added to the kind of std namespace called the mutex. So to create one of those, I just say, and if I had the using line here, I could get rid of that. I could just say mutex, mutex1, create that in the global space, just like I do it with Pthreads. But notice it's its own type now. And then to lock it, I do mutex1.lock. To unlock it, mutex1.unlock. And then I have my critical section kind of in between the lock and the unlock. So relatively straightforward to use. And again, we can make as many of those mutex variables as we want. and we can use them in as many functions as we want. So very simple to use mutexes. Now, condition variables, I'm not going to go over those right now, but they kind of are part of a collection of other primitives that are supported in C++11 and beyond. And notice we have mutexes, which we talked about. There are also some other forms of mutexes, timed mutexes, which is like a mutex with a timeout. It's kind of like using a lock in Python with the timeout parameter set to something other than none. We have these recursive mutexes, which are like rlocks in Python. We have recursive timed mutexes, which are like rlocks with a timeout. And then we have these lock guards, a unique lock, condition variable, a condition variable any, which can associate with any lock type. Condition variables have to associate with what's called a unique lock, which is up here. But the idea behind these are all synchronization mechanisms. And this lock guard thing is actually pretty cool. That allows you to do a scoped-based mutex ownership wrapper. In other words, a lot like a with block in Python that we saw before. You can make a lock guard section that you put the lock in, and then that scope, when that falls out of that scope, the lock will automatically be released. Unlike what we had to do back here, where we explicitly locked and unlocked it, we can make a lock guard, put the code inside of that scope section of that lock guard, and that would release automatically, like a with block in Python. All right, now, a couple final things here, and then we'll be done for today. Is there a few other concurrency features in C++11 and beyond? The first one, locks, we looked at. There are other types of locks where you can, there's a method to try a lock to see if it's locked or not, kind of like a checking to see if it's locked. There's some other things with locks that I'd encourage you to look up. There are condition variables, which we talked about. There are also futures and async, like we saw in Python. There are latches and barriers. There are semaphores. There are also some parallel algorithms that are built in the C++11 and later versions. And for details on that, I would consult this kind of URL that we have here, the cplusreference.com. And they have a whole description of a lot of these features in there, along with the details for how you use them, example code. And then if you're interested in writing straight C code and not C++, C11 has those same kinds of things here in this. And let me just quickly go to that and look at each of those. Let's start with, here, let me go back to here. Let me go to this C++ documentation first. So let me switch over to the main window here. Okay, so looking at this is kind of the C++ thread support when you click on that link. And you'll notice there's a whole bunch of stuff in here. There's like the defer lock, try lock down here, adopt lock. There's a whole lot of stuff that you can do here. Also condition variables, you can check the status of them to see, list the possible results of timed waits on those condition variables. Semaphores, notice the semaphore stuff was not added until C++20. So you have to have a compiler that supports that to have semaphores built into the language. But notice there's async, there's futures and shared futures and async. All of that stuff is in here. And that works similarly to how it works in Python. But there's quite a bit of stuff in here that I would encourage you to take a look at. Now, looking at the C documentation, notice that for C11, threading is built in. So as a thread type, thread create, thread exit. This works, a thread join. This works a lot like Pthreads, but without having to use the Pthreads library to access that. So this is part of the C11 standard on threads. So what you'd have to include there is threads.h rather than pthread.h. But notice that there's a lot of stuff that we're used to here, including mutexes, condition variables, and I would encourage you to look at that documentation when you get a chance. Let's switch back over to the slides for a second. All right, so I would encourage you to take a look at those things in that documentation. And then really that's all I was going to cover today. I would encourage you to play around with like some Pthreads code, rewrite that code using that, and I would say something like that garden problem that we did previously might be a good thing to look at. And other than that, that's all I was going to cover today. So stay safe, and we've only got one lecture left. I may give you free time to work on the labs and get those done and ask questions. I may make a Blackboard collaborate session or something like that to talk to you guys through that. The final exam will be on the date that the final exam is scheduled for, which is in the second week of final exams. So take a look at that final exam schedule. And if you have any questions at all, ask them in the comments section here, or send me an email. And I don't think anybody has posted in the kind of comment thread section of the course page, but if you have questions, any of those places, send me a text or an email, or give me a phone call. All of that's good, and I'll help you answer your questions. That's it.